Hello everyone. In this video we look at the second step in the metal extraction process, which is conversion of the other chemical forms of the metal into the oxide form. So when we talk about the four stages of metal extraction broadly, we have the first step, which is the concentration or enriching of the ore. Second step is converting the other type of ores into the oxide form. So we'll take a look at why do we need to convert the other type of ores into oxide form. But broadly here we have two steps. One is roasting, second is called as calcination. The third step will be reduction of this oxide form of ore to get the metal, and the fourth will be the refining of the metal. In some cases we do see that the second and third might happen together. So that's in the case of substances like copper, but we'll take a look at it when we go to the specific example. Now, talking about why do we need to convert the other type of ore forms into oxide form. So generally whenever we look at the reduction is basically the removal of oxygen from the oxide, or if you have a sulfide form, removal of the sulfur. If you talk about the explanation of this reduction, when you look at any metal in the combined form, so whenever a metal is in combined form, we know that a metal will be having a positive. It may be a unipositive or dipositive or tripositive. When you get the respective metal, the oxidation state of metal in the free form or the natural form will be 0. So what essentially we are having is a reduction or decrease in the oxidation number, and that is what we call as reduction. So while we generally say reduction is a removal of oxygen, broadly speaking, whenever we look at any metal compound, metal will be in the positive oxidation state, and when it comes to the metal form, it will be having a 0 oxidation state. So the decrease in oxidation number is what we call as reduction, and hence whenever we look at getting the metal from the respective ore, it will involve a reduction step. And when we look at the presence of the metal in the combined form, it may be in the oxide form, it may be in the sulfide form, it may be in the carbonate form, it may be in the phosphate form, or it may even be in the halide form, where X can represent a chlorine, fluorine, bromine, and sometimes the compounds might even be having the water molecules, which is the water of crystallization. Now when we want to get the metal reduced thermodynamically, we look at the delta G for the feasibility of the reaction. So delta G will be equal to delta H minus T delta S. So for every spontaneous reaction, del G will be negative, and non-spontaneous del G will be positive. So for the spontaneous reactions, del G will be negative, and in most of the cases the reduction of the metal will be non-spontaneous, which means for those reactions del G will be positive, and it means that we actually have to supply energy to make this reaction feasible. And we see that the reduction of an sulfide or a carbonate or a phosphate or a halide form, for them the del G will be more positive, which means we have to spend more amount of energy to perform this reduction. Whereas in case of the oxide form, it is thermodynamically relatively easier to perform the reduction. That is the reason why we will be trying to convert the other ore forms into oxide form before we perform the reduction. And having understood the importance of this conversion to oxide form, what are the methods that are available to convert? So if you look at a sulfide ore, when we strongly heat this sulfide ore below the melting point in the presence of excess air, then we will see that the sulfides will be converting themselves into the oxide. So here we are looking at the example of zinc sulfide. On heating with excess oxygen, you are able to get zinc oxide. But if you have lesser amount of oxygen, then we may end up getting some other substances like zinc sulfate. Okay, and it is very important that we have this heating below the melting point, not above the melting point, below the melting point with excess oxygen. thereby we will be able to convert the sulfide ores into respective oxide form. Okay, and it also happens that in this process sometimes the impurities of non-metal, okay, so they may be getting vaporized because their oxides might be volatile. So this is another advantage of this roasting. So roasting is essentially heating of a substance in the excess of oxygen below the melting point of the ore. The second step is calcination. So calcination is strong heating in the absence of oxygen or limited supply of oxygen. Now the calcination is used to get the oxide form from carbonate ores. Like in the case of calcium carbonate, if you are heating strongly in the absence of oxygen, we will get calcium oxide and carbon dioxide gas will be liberated. It is also used to obtain the oxide form of the ore from the hydrated oxides. Like in the case of bauxite, when we are leaching alumina from bauxite, we see that we will be producing hydrated aluminum oxide. So on heating hydrated aluminum oxide, we will be able to get alumina or Al2O3. So this is the method that can be used both for the carbonate type of ores as well as for the hydrated oxides. So this is about the calcination. So these are the two important processes that will be there to convert the other type of ores into the oxide. Now once we have the oxide form of the ore, we will be able to reduce this to get the metal, and that we will be seeing in the third step of the metal extraction process.